I will briefly show you a study case of two minarets in Azerbaijan. These are two masonry minarets. The left one we will call the taller minaret, while the right one is a lower minaret. Both of them has been already decapitated by a seismic event. And here we see some picture of the inside. And here, let's focus on the taller minaret. The taller minaret is characterized by some evident cracks, diagonal cracks in this zone and in this other zone. And we can see here from this picture, evident horizontal cracks induced by seismic event. Here again, some cracks in the inside part of the minaret, in the rigid core of the stairs. And here again some evident cracks in correspondence of the stairs. This is a vertical cracks and this is the diagonal crack, the same that we seen in the previous slide. In order to evaluate the state of stress inside the minaret and to evaluate the displacement of the structure subjected to a seismic event, a finite element model has been adopted. The finite element model was modeled even the stairs that was inside the minaret, and here some result in terms of principal mode of vibration of the structure. So we see that the first mode here is a typical flexural mode, so that the tower moves up and down, and then the second one is a torsional mode, and then the third one is a typical combination of a flexural mode and a torsional mode. Here is represented a state of stress, vertical state of stress inside the tower subjected to horizontal stresses. And as we can see, there are some regions, for example, here and here, where the compression state of stress is very high. At the same time, we have other regions, for example, here and here, where the state of stress is in tension and very high. Here are represented again the state of stress in terms of horizontal stresses, and again here we can see some peak of horizontal stresses, and we see, for example, a peak of horizontal stresses here and some peak of stresses in this point and this point and again here. Of course, if we superimpose the state of stress with the crack pattern, we can see that there is a straight correspondence between the peak of stress obtained numerically by the finite element model and the crack pattern that has been observed during the recognition. So, for example, the same peak of stresses that we saw here in the model has been detected also during the recognition. Let's consider the lower minaret. The lower minaret presents just an horizontal crack in this area. In this area, just one horizontal crack induced by shear forces. And then it presents some deviation of the bricks induced by torsional effects. So that, again, the lower minaret torque in case of a seismic event. And so, again, a numerical model is able to represent this effect, this torsional effect. Let's move now to the consolidation intervention that has been proposed for this minaret. Few criteria of intervention that we usually follow in our intervention. These criteria are necessity, efficacy, compatibility, reversibility, durability, and of course each intervention must respect the existing. The aim of the consolidation intervention is an encirclement of the structure. This encirclement, this confinement, can be done either from outside or from inside. There can be different type of encirclement. In the past, the encirclement was done by using these iron rings on the external part of the structure, and these rings were able to confine the structure. Nowadays, some other material are used. For example, the use of fiber reinforced material. We can see here the consolidation of a chimney here in Italy, where some strips of fiber reinforced polymer has been adopted. The question is this intervention respectable of the existing structure? Is this intervention a reversible intervention? Is this a minimum intervention? Probably this is not a minimum intervention, so probably is not necessary an intervention like this. There can be some other possible way of intervening on a structure. So, for example, another possible solution is to use steel cables. We see here a minaret again in Azerbaijan that has been consolidated by using this steel cable on the external part. This is just a temporary intervention, but as we can see, this is a light intervention, is respectful of the existing and even is removable intervention, so that at the end, if it is not necessary, I can take my cables and remove them without causing any damage to the structure. Concerning our minarets in Azerbaijan, a first proposal is to use steel cables. Use steel cables in this area, the most cracked area, and these steel cables are placed inside the joints of mortar between the two bricks. This technique of using steel cable has been tested by numerical experiment conducted by Professor Lorenzo Iurina, and here we see two specimens. These are two brick columns. This one is without any encirclement, while this one has small stainless steel cable inside this joint of mortar between the two bricks. As we can see, the two columns has the same aspect. So this is a minimum intervention. So concerning this experimentally campaign, several types of specimens were tested. The specimen 1 and 2 without any cables, specimen 3 and 4 with cables in alternated joints of mortar, and then cables in all joints of mortar in column in number 5 and number 6. Here we see some the procedure that must be followed to do this intervention. So this is a brick, this is another brick, this is the mortar between the two bricks. A small portion of mortar is removed, then a thin layer of fiber reinforced mortar is placed, and then the wire, the steel cable is placed inside this layer of mortar, and then this joint is closed again. The advantage of this system is that it needs a small space between the two bricks, and it is an active system. So it starts working since the very beginning, since the steel cables are post-tensioned. Here we see some picture of the experimental campaign. So here we see the wires, the stainless steel wires inside the mortar. These are 3 millimeters wires, so very small. The test consists in measuring vertical displacement, horizontal displacement, and radial displacement. And from the result, we can see that not only an increase of strength is obtained by introducing this wire, but even an increase of ductility in the specimen is obtained. So that you see, this is the collapse load of the column. Without any cables, we reach a collapse load. With cables in alternating joint, an increase of more or less the 50% of the collapse load, and the cables in all the joints, we reach the 95% increase of collapse load. So it's a strong efficiency. Even the collapse mechanism is different. Here, the specimen 1 and 2, without any circular confinement, we see the typical vertical crack of a masonry structure from outside and again from inside. But if we insert these wire cables, we reach a different, we increase the collapse load and we reach a different failure mechanism, so that we reach the collapse of the brick if there is a partial confinement. We reach the collapse of the brick and the collapse of the wires if we introduce a complete confinement of the specimen. And then a second proposal has been advanced for our minaret. The second proposal consists in placing a steel ring inside the masonry minaret, so that this is a steel ring that is connected to the masonry structure by means of these small bars. These small bars inside the masonry are connected with the steel rings by means of bolts, so that by closing these bolts we obtain a confinement of the masonry. Again, this is an active system of consolidation that is inside, so from the outside we can see anything, and this is a typical minimum intervention that is respectful of the existing. Again, if we introduce these steel rings and again a spheroidal plate in steel, we can introduce also this horizontal element, and this horizontal element are simply steps, so that if we have a simile without any stairs inside, we can introduce this steel structure that has a structural function on one side to that increases the strength of the tower. On the other side, we can have stairs to climb up the structure. And then here another method of consolidation, and it is called REM, reinforced arch method. It consists in placing some steel cable either on the extradox or on the intradocks of masonry structures as arches, vaults, and dome. Several tests has been performed on this arches, this reinforced arches method, and for example, large scale test here on more than 100 real scale masonry arches, where steel cables were placed on the extradox or on the intradocks. Again by Professor Iurina, a reduced scale test has been performed on wooden arches that has a span of 1 meter, more or less, and these arches has been tested by applying vertical loads in different points and by applying different geometry, so circular arches, Gothic arches, and so on. Again, the third experimental campaign conducted by Lorenzo Iurina has been performed in 2011, and the same wooden arches has been tested by applying some horizontal load to simulate some arches with a seismic acceleration. Here again the same arch. These cables are the cable that has been used to apply the horizontal force, and this cable inside here in the intradocks are the post-tension cable that coincide with the reinforced of the arch. And this is the collapse of an arch. What is interesting is to say the experimental results obtained in terms of strength We see on this graph, on this axis, on this vertical axis, the collapse load of the arches. On this horizontal axis, the tension applied in the cable. As we can see, the relationship is linear, so that more tension we apply in the cable, more increase of collapse load we obtain. These are the curves obtained with different arches. This technique has two limits. The first one is the limit induced by the crack of the brick by compression. So I cannot go farther than a certain value with the tension in my cable, otherwise I break the masonry and I broke the brick. And the second limit is given by the resistance of the steel cable. So I cannot go farther than the resistance of the cable. And this technique and this result has been obtained both for extradoxal cable and for intradoxal cable. What is interesting to say here, just 3 seconds, it's interesting to say that if this collapse load is a seismic load, it means that I can consolidate my arch by applying this post-tension cable. I can consolidate these arches and I can reach a larger value of seismic collapse load so that the structure can be adequate to a seismic event. Here are some examples of the intradoxal cable applied here in a city near Milan. Here and here, the stainless steel cable on the extradoxal bolts. And here we are in province of Lodi, not far from here, where some steel cable have been placed in the intradox of the arch. So the second solution. And then, just to close, this is a tomb here in Milan, and this tomb with this typical shape has the mausoleum that we seen a few minutes ago, has been consolidated by inserting a steel cable in here. So again, a steel cable post-tension has been adopted to give the confinement to the entire structure. Further information on this website, urina.it. Thank you.